Hi all, we're going to look at a viewer suggested problem today, so thanks Derek Liang for this problem suggestion. Right, so I'm looking at this for the first time, so we'll solve it together. Take a look with me. So we have this tree, fine, and the vertices have numbers on them, and we want to find a subset that within distance k with the maximum total sum of weights. So everything's within distance k of each other. Okay, and there's at most 200 nodes in the tree, and they can be at, up to, k can be up to 200, and the weights are up to 100,000. So, okay, how is this going to work? So how does this example work? They don't give us information. It'd be nice if they drew out the example. Okay, anyway, so this is just a path, and we can pick basically any 3 consecutive nodes. 1, 2, no. I need 2 consecutive nodes? Wait, how do we get 11? Oh, they have to be far apart. Okay. How do we get 11? One, two, 3, 3 to 4, oh, 3 to 5. Okay, so we can pick what, 5, 4, 2 in this case? Okay, and in this example is going to be too hard to think about. Okay, so they actually have to be far apart, not close together. So if you pick, if k is 1, then if you pick a node, you can't pick its parent. If k is 2, if you pick a node, you can't pick anything with a distance 2. Okay, so this is going to be some kind of tree DP. Let's jump into coding and see how it goes. This is problem F from a div3 round, by the way, so it's the hardest problem and the easiest type of contest. So first we have the weights, so we'll call them W, so we can read them in. So I don't know how to solve the problem yet, but no harm reading in the input. We're definitely going to need this code. So we can read in A and B, and they're probably, so they're 1 index in the problem, I remember from the example. So we'll just 0 index them. And why don't we just, okay, so the basic structure here is we're going to have a DP, right, for our current node. And I think this is going to be the distance, Okay, so node I is the index of current child. I'll explain what I mean by that more in a bit. And then D is closest node in set outside subtree. Let's call this X. And then there's also going to be, right, so let's just say k is some global variable. And we're also going to have the set of edges. maybe a set of children. Maybe we'll just call that, all right. Okay, I'm gonna do a quick break. All right, I'm back. Something like this. Okay, so the tricky thing here is going to be formulating sort of the DP state correctly, and also, you know, how to calculate, how to calculate the answer. So, what, by the way, what is this trying to say? So, is the maximum subset sum I can get by picking nodes from the first so I think it's very useful for DPs to actually define exactly what subproblem you're going to use. Right, so so that's what I'm trying to do right now, is to write down exactly what this function is supposed to mean. Right, so what is the concept here, by the way? Is that ultimately the answer is going to be dp 0, 0, -1, I guess. right, so if you look at this definition, like this is going to compute the final answer for the entire tree, and the hope is that if we pick the subproblems correctly, right, we can solve these things in terms of smaller instances, smaller recursive calls to the same problem. Right, we're going to basically like recurse on the children. And so the total number of calls is only going to be, there's n of these, and then there's k possible distances. So the total number of calls is going to be something like n times k. And so as long as we can resolve each call in like O of n time, this will run quickly. That's the general sort of concept of, I guess, DP in particular and tree DP in particular. Sorry, DP in general and tree DP in particular. Let me just add the usual header. Okay, so what we need to decide is how much we're going to restrict the ith. Right, so we're going to build dp xid out of basically dp x c of xi. So that implies that we're going to want a C array. Right, C xi is the ith child of x. Maybe not then a parent array. We also need the weights, presumably 0, and we'll figure that out. And we're also going to xi plus 1. Right, just a sneak preview. So this is the sort of raw materials that we're going to use to figure out the solution to this problem. Well, I say actually this is also in question. So the basic idea is going to be so the basic idea is we're going to say right, so these two subtrees partition this subtree, or this, anyway, subset of the tree. And so we're going to pick, a maximum subset from both of those places and then combine them to get the answer for this subset. So, by the way, what do I mean when I say that this is a subtree? Well, yeah, so this just defines some subset of nodes of the tree, right? It's the subtree rooted at x without its first I children. And so this is the subtree of the ith child, and this is the subtree of x without its first I plus 1 children. Right, so that's why it partitions, right, is because we're sort of just picking off like one child, basically. So how are these going to combine? Well, so what we want to say is we're going to pick, the best subset in this child and then the best subset in everything else, and then we're going to stick them together to get the best subset for this call. But so the concern there would be that we might, even if the two subsets independently obey this condition about k, that no two nodes can be within distance k, some node from this guy might be close to some node from this guy. So that's what we need to worry about when we're combining them. And so the way that we're going to solve that problem is by saying the closest node that that this guy can pick is like some number of levels down, right? So here we have, let's kind of try and draw it out. So here we have x, right? And here's its ith child. And this has some whole subtree. And here's some other subtree. And so the bad thing that might happen is if you picked this node and this node, then they're at distance 2. So the way to solve that is to say, okay, well, let's say that the distance that we need to stay away from is 10. So this guy, you can't pick any node in the first 5 layers, and this guy you can't pick any node in the first 5 layers, and then we know that they'll be distance 10 away. And actually, is 5 and 5 like the right kind of thing? Well, no. We said even if we pick the 0th layer and the 0th layer, they're still at distance 2. So actually, because of these 2 edges, we can do anything sort of up to, we need to partition out basically k minus 2 from both of these. Right? It's the restrictions that they have to live with. So ants equals, and then we also have to think about whether or not we want to include x itself in the subset, which we will do separately. Okay, so one possibility is that you could do dp of the, go down to the child, and the child has to stay at least k1 away. And also the rest of the children, and they have to stay at least k minus 2 minus k1 away. Another possibility is that you could just include x itself, so that gives it wx, and then the child, well, you have to stay at least k away, and also anything in here you have to stay at least k away. And of course, this is going to prevent you from choosing, x again, because it's 0 away from itself. And also, we should write but you can only choose. Right, we also have a restriction on ourselves coming in from above or from the left, so we need to respect that restriction. We can only choose the root if we're totally unrestricted. Right, so maybe I should use 0 to represent no restriction. That seems cleaner. Okay. Right, so I said we needed the C array, which I haven't computed yet. This is what this root function is meant for, so let's just do it here. So we need to know what the children are. And we don't want to go back to our own parent. So C of x, so y is a child of x, and also we can go descend into y. E now is just a local variable because we're replacing it with C. Okay. So this compiles, I think. Like this is like a a plausible first try, so I'm just curious if it'll work. Probably there's some bugs. The main thing that's missing is the memoization here. So to get DP to run fast, you need to we're making a lot of recursive calls to this function. The sort of key insight of DP is that you don't... What am I trying to say? That this is going to return the same value every time if you call it the same arguments. So instead of computing the same things over and over and over, we need to remember what we computed before, and if we get the same arguments again, we can just look up the answer. So I'll show that later. But for now, this case is so small that even the very inefficient thing would work if it was correct, but this is not correct. So what are the problems? Well, one problem is that we're going to run off the end of this array. So that's not good. So if I is cx.size, then the only thing that we can do is possibly pick x. And if, is this always non-negative? Yeah. So if b is 0, then we should just pick x, and otherwise we can't pick anything at all. So I'm just going to print out, right, so we got the wrong answer, so now we need to figure out what happened. So I'm just going to do some debugging. We said that we wanted to start at 0. This k meant to be 1. Okay, so this loop never runs. That seems like a bug. So if k is 1, then putting 0 in both of these is valid. But if k is 2, then that's not valid. Okay, so I think I was off by 1 here. Also, k is at least 1, right? Yep. Okay. Okay, so this is claiming that we can take all of them. So that's not correct. So let's actually print out what we got from each of these calls. And it's maybe nice if we just have a single point of return. Let me just restructure the code that way. So that way we can see this print for even the sort of base cases. Two index 1 d equals 0. Right, so that would be 5 plus 3, but that's not meant to be allowed. Why is that happening? This seems wrong to me. This says if you can only pick among 3 and 5, there's no restrictions, then you can get 8. But you can actually only get 3 or 5. You're not supposed to be able to take both. Right, okay, so the restrictions mean something a little bit different in these two cases. Because if I say 1 here, that means I'm not allowed to take the child. But if I say 1 here, that means I'm not allowed to take x. And actually, in this case, this is the case where I take x. So this is meant to be the case where I can't take x. So this should always be, this is always meant to be greater than 0. I think it should look like this. 11. Let's try this case. And that's 6, so that's wrong. Here we have k equals 2. Maybe I should try and work out what's going on in this case. Okay, so we have 1, which is attached to 5, and 3, and 5 is attached to 7, which is attached to 4, which is attached to 6. And where's 2? 2 is attached to 3. So I think the graph looks like this. And I'm actually just going to write the weights. Yes, this is 2, 1, 2, 1, 2, 1, 1, and k equals 2. So we should pick this, this, and this, I think. Okay. Actually, look at what we did. That might have been the most helpful view. Yeah, I think it was not. So this was one is attached to 5, and also to 3, and also to 2. 5 attached to 7, which is attached to 4, attached to 6. Okay. And these are all sort of off by 1 because I decided to 1 index instead of 0 indexing, so let me just correct that. And I'll just mention what the child is that we're looking at, which should help the output be a little more readable. of bounds. Okay. So if we're just looking at 6, then the answer is 1. I agree. If we're just looking at 7, which has a single child of 4, no, it doesn't. Right, so 4, looking at its child of 6, still 1, fine. Okay, 7, looking at a child of 4, so that's just 7, 4, 6. That's 2, because you could just pick the 7, fine. Uh, 5, looking at its child of 7, you can pick anything. So that's 5, 7, 4, 6. So that's all of this. You could pick anything. It's claiming the answer is 3. I think that's right. You can pick the 5 and the 6. So if this seems wrong. Yes, okay. So I didn't properly propagate the constraints from above. So this, we can't pick anything with depth less than d. So regardless of what kind of recursion we're doing here, we do have to respect that constraint. So this is actually std max d minus 1 in k, and this is std max d, because we're again, this is actually descending into a child, so you get d minus 1. This is staying put, so it's d. Okay, and now we get 4. So this might be correct. Let's be lazy and just try to do a map, which might better go right away with. So if let's see, x times, oh, so n times k let's just be nice and be lazy. This is sort of the simplest way to set up a DP, is we're keying it by these arguments, like we said. And so if we've already seen those arguments, return, this, what we already computed, and at the end, when we actually have to do some work, write down that we computed it. So with the next time we see those arguments, we don't have to do the work again. So we can just check that we still get the right answer, and we need to include a map. This is a hash map. Actually, this is a tree, so it can take arbitrary keys. So we do get 4, we do get 11. So let's see if this is right. Gosh, where am I? Okay. Yeah, I think this is probably a bit hard to follow, especially if I haven't seen Tree DP before, so I'm going to go over it again. I'm just curious if it's right or not. Well, it's a good sign so far. I'll check back in a bit. Right, so what was the concept here? so I guess the first thing was to recognize this might be a DP problem. Derek sort of mentioned that in his suggestion, so I had a leg up there. But I don't know, things that these like trees and distances are basically, if it's a tree DP problem, if there's some way, sort of from some information about the children, right, if there's some value that you can compute in the subtrees, such that from the answer for the children, you can compute the answer for the parent, because then you can just start at the leaves, compute whatever you're computing, and then for all their parents, keep sort of pushing the values up until you get to the root of the tree and you have your answer. Wrong answer on test 9. Oh no. Okay, in a contest we would not actually be able to see this information, but we said something that was a bit too high, so we did something that was meant to be impossible. Right, because we picked something that was better than it actually could have been picked. Okay, so we need to debug that. Okay, so anyway, I was saying that, yeah, so this problem looks like a problem that you could do with tree DP. It has like distances and like a sort of maximum independence set, like a very classic tree DP problem, which is sort of a simpler, this is a generalization of it, is you want to find the maximum independent set in a tree, that is the maximum number of nodes you can pick, such that you don't pick any node in its parent. So that's the case where k equals 1 and a is 1 for every node. That's that problem. So this is sort of a generalization of that problem. So maybe you can also solve it with tree DP. Yeah, so this is just reading in the input. This is a good way to represent all kinds of graphs. It's just an adjacency list, right? So for each node, what are its edges? This would work even if it wasn't a tree for an arbitrary graph. And then for a tree in particular, you often want to root it arbitrarily. So this problem didn't come with a root, right? That doesn't really matter. There's no top node in this tree, but it's often helpful for trees to think of them as roots, so you can talk about like parents. So I'm just going to call 0 the root and compute, instead of a set of adjacencies for each node, just a set of children, which is the same thing as what's adjacent to it minus the parent. So the way I do that is I pass, start rooting at 0. 0 doesn't have a parent. I pass through the edges. And then for each node, right, so we're at some place in the tree. We know what the parent of that node was. For every node connected to it, if it's not the parent, then it must be a child. So write down that it's a child, and then recurse into that child. And we are the parent of our child. So that gives us sort of a directionality to the tree. Right, for any now instead of for every node we can enumerate its children, and then we can actually try and execute the DP, which I've apparently done slightly incorrectly. And so as I tried to explain earlier, the state of the DP is that we're going to say that we're thinking about a node and sort of some suffix of its children. Like what's the answer for that? And we also need to keep track of this restriction that may have been imposed from outside, from what we've already done so far. So the general idea for DP is that you sort of try all possible choices, and that's what we're going to do. So why do I need to have this like going through the children one by one thing? Wouldn't it be nicer if the state was just x, right, the subtree of x? And it would be, but it's a little bit trickier to do that because then you need to sort of worry about collisions among like all of the paths, all paths through all possible children going through X. Which I think you could do, but it's just easier. It is, and it's often true that it's easier to iterate sort of through the children to keep track of which child you're on, so that instead of trying to handle a whole sort of level at once, you're just trying to handle one child at once. Right, so instead of worrying about a conflict between the first child and the last child, I just need to worry about a conflict between the current child and the rest of the tree. And the children to my left are being handled by this, this parameter. Okay, so let's actually try and figure out what our bug is. Okay, so the DP stuff is fine. So it's in here. So what are we saying? We're saying if we're sort of done with all the children, then the only thing we could possibly do is pick the current node, which we can only do if we have no restriction, d is 0. So then we can pick the current node and get whatever its weight is. Otherwise, we don't get to pick anything. We are stuck with 0. So otherwise, there's two possibilities. We can either pick our parent, potentially, if d is 0, or pick x, the current node. And in that case, everything that we pick, both from our child and from sort of the rest of our children, has to be at least k away. Should this be k minus 1? No, this should be k plus 1. Right? Because 0 means that there's no restriction. So 1 means that you can't pick the current node. Yeah, so if k is 1, this wasn't big enough. Because 1 means you can't pick the current node, but you could pick any of its children. But the current node is still x here. So if we pick x, if k is 1 and we pick, we pick x, then we can't pick any of the children of x. So this should be k plus 1. So I think that was the bug. Whereas for the child, we can, if k is 1, then we could immediately pick, no, we can't pick the child, but we can pick anything, its children. So that's what, that's what the 1 would represent. Yeah, so this is the case where we pick x, and then we can't pick anything sort of k away, anything in the first sort of k layers of the child, and we can't pick anything in the first k plus 1 layers, right, including x itself, in sort of the rest of the children. Okay, and the other case is where we don't pick x, and then we only need to worry about sort of paths, come up through the child and collide with other stuff. And so the point here is that, right, so we're considering, things restricted to CI, and then also things restricting to X and sort of the rest of its children. So this edge is always going to be between them. So that's one distance that we sort of get for free. And so there's k minus 1 other, more distance to dole out. Because we have to make sure that, the closest thing here and the closest thing here are at least k apart. So they're already 1 apart. Now we have to say, okay, well, you have to, they have to be k minus 1 more apart. So it can either come from here, or it can come from here. So that's what we're looping over. So right here we're saying, pick the maximum thing in your child, which is a distance at most, however far apart we need for the internal path here to not be a problem. And also we have this restriction from outside that we need to respect. But again, we're going down this edge, so that's why it's d minus 1, because we've already paid sort of 1 to that external restriction. And then there's sort of the rest of the children who, we are sort of still starting at x, so we haven't gone down at all, so it's, there's no d minus 1, and we can spend the rest of the k minus 1 on this. So should it be k minus 1 minus k1 instead of k minus k1? Okay, well, let's say k is 1 and k1 is 0. That means we can pick this guy. But we can't pick this guy still. So this, I think, should be k minus 1 minus k1. Right, if k1 is 0, such a bad name. How about kc? If kc is 0 and k is 1, then we still can't pick x because we might pick, ci. So that means this needs to be 1 and not 0, so it should be k minus kc. Yeah, that seems right. 11, 4. Okay, we submit. Yeah, so the tough part of the DP is getting these sort of intricate cases, right? Right, you just have to think about all the possible things you could do. Pick x is one case, and then don't pick x, but then you have to worry about these paths that cross this edge that might interfere with each other. So the subproblems are like mostly independent, but they're not totally independent, and that's where the tough part of the DP comes in. Test 43, that's a good sign. Yeah, I think that's pretty much all there is to say about this one. Hopefully, this was a good example of a tree DP. I think it was. Time limit exceeded on test 69. Okay, well, I guess there's more to talk about then. So let's try and speed this up. So probably the worst thing that's happening here is this map. Maps are just like really slow. So I'm going to do the thing that I usually do, which is faster but uglier. So instead of sort of using this arbitrary key, we're going to map it into a sort of denser thing. So what is that going to be? So if I cx.size, then okay. So this part's a little magic. I'll explain in a little bit. But again, so we're finding some key that that hopefully identifies the state. And if we've seen that key before, then return, whatever we had for it. Write down that we've seen it, and at the end, write down that we actually computed something for it. Yeah. So dp is a vector of length, let's see. something like that. That's DPS. So we need to figure out how big our DP array needs to be, which again I'll talk about in a moment. And then we just initialize it. So initially we've haven't seen anything, and so we just write down some arbitrary thing here. In this case, we know that all the answers are non-negative, so we could actually just make this. In fact, I'll just do that. We can use negative as a sign for we haven't seen it. So sure, let's do that. We don't need DPS. In general, like if the answers could be negative, you can use this extra array so that there's no confusion between like a not seen value and an actual computed answer. But negative is fine for this problem. Okay, so what is the idea here? So you want to make this number small so that you don't have to use so much space storing your DP table. So typically the way that you do that is right, so how do you translate like ABC to an integer? Let's say 0. Right, there's these restrictions. Well, you sort of think about it in like base, it's almost like a base conversion, right? Like how does, if you had 1, 2, 3 as your state and they're all at most 9, then the integer should just be 1, 2, 3, 123. So in this case, A, like literally, like A represents sort of this much, right? Like you can think of these units as like C plus 1, and these units as B plus 1 times C plus 1. So you can write it down like that. And so the reason why this is unique is because it's the same reason like normal numbers are unique. That A equals 1 gives a bigger integer than, like 1, 0, 0 is bigger than 0, BC. That's the kind of, that's the condition that you want for uniqueness. Yes, this is normally how you do it. And you also, right, so you want it to both be unique and also dense. And so the density, well, how many possible things are there? There's A plus 1 times B plus 1 plus C times C plus 1, right? Just values, values, values. And this, generates all the numbers between 0 and that upper bound. So this is, anyway, it's a good way of converting a tuple to an integer. In our case, we want to do something a little bit trickier because like this looks like it's n squared possibilities, but actually this like uniquely picks out an edge of which there's only n minus 1 of them. So instead of spending n squared space memory to sort of store the state, we can actually get away with n. So that's why I'm trying to be clever here. So I thought it's almost just the case that you could use CXI, but we're allowing I to be equal to, past the last child, sort of. So we need to handle that too. So I'm just saying, if you're at the last child, then your sort of vertex that you're at is 2x plus 1. So there's the odd case. If a vertex is odd, that means you're at its last child. And if it's even, that means that you're just at it sort of as a child. And then D ranges from 0 to k plus 1. So it's k plus 2 values, so that's y times k plus 2, and then just plus D. So that's my sort of state compression. And how many possible states is that? Well, you know, each vertex shows up as even and odd, so there's 2n of those, and d we said was k plus 2, so that's my DP sets. And you know, how do we know that it's big enough? Well, this can be at most 2 times n minus 1 plus 1, so, which is 2 times n minus 1 plus 1, which is 2n minus 1. And this can be at most k plus 1, so that is the right value. So this should make it a lot faster because like going through maps is much slower than going through arrays. I maybe could have tried like unordered map, just a hash table instead of a tree. Might have also been enough. Let's see. Yes, n is not a real thing. It's lowercase n. And this is supposed to be a vector of long longs, not a vector of ints. Okay, so 11 and 4. Fine. Let's try submitting again. Huh. Really shocked that we managed to run out of time. Oh yeah, right, sorry. So this loop is, so the total runtime is like nk squared. Okay, so that's kind of reasonable, because they're both up to 200. Okay, and we're accepted. Cool. So yeah, definitely some tricks in this one. Compressing the state space, not obvious. And just sort of how to set up and do the DP, not too obvious. But yeah, cool problem. That's it for now.